So I'm going to draw the Lewis dot structure super fast for you. Okay? So it looks like that. So we said that this was AX2E3. Right? Now, it is an ion. So ions, polar and nonpolar, does not apply to ions. Okay? Polar, nonpolar. But we said, notice again this one, what's unique about that?
It's one of the exceptions.
For what?
For the central atom having a lone pair.
In other words, this is going to be a linear, symmetrical molecule. So if it didn't have the charge, if it was just neutral, this would be symmetrical. Even though there's lone pair on the central atom, we would still consider this to be a nonpolar molecule because it's symmetrical. But again, it doesn't apply because it's an ion, so we just kind of go from there. Okay, so I have this. Okay, now, that looks symmetrical, but all the bonding atoms the same. So what's the rule? Is it symmetrical or asymmetrical? It's asymmetrical. Okay, and it's got phone call in it. So what does phone call mean?
There's a polar bond.
It's got polar bonds. It actually has 4 polar bonds. Okay? But they're not pulling equally. Fluorine pulls way stronger than chlorine does. It looks symmetrical, but you always have to realize that those molecules, it looks like this. Get out of the light. It looks like this. So even though it looks like they're right across from one another, this is 2 dimensions, but the molecule is actually 3 dimensions. So the chlorine is pulling this way and this way, but the fluorine is pulling this way and this way harder, so it's getting pulled more that way than it is this way. So you got to trust the rule that, okay, even if there are no lone pair on the central atom, if all the bonding atoms aren't the same, it's going to be asymmetrical, even though it looks symmetrical in your drawing. Are y'all with me on that? Okay. We're going to talk today about the properties, why this is important, because it all determines the properties. So it has polar bonds and it's asymmetrical. What does that mean about the molecule then?
Polar.
It's polar. Okay? Now, NF3. Looks like that. So is that going to be symmetrical or asymmetrical? Asymmetrical. It's pyramidally shaped. It's an asymmetrical shape. Does it have polar bonds?
Yes.
Yes. Now, this is one of the big 4 as well, but fluorine is 3.98. This is 3.0, so we have a difference of 1. So it's still got a pretty significant difference. So it's going to be polar. If fluorine's involved, it's going to be polar. Fluorine does not share well with others. BRF3. I think it looks like that. Isn't there 2 lone pair on the bromine? Okay? And then all the lone pair around the fluorines. So this is going to be symmetrical or asymmetrical? Asymmetrical. The shape is T-shaped. Okay? But it's got, you look at, again, the lone pair are not what's making it asymmetrical. The shape makes it asymmetrical. It's just that most asymmetrical shapes contain lone pair. So it's just a shortcut for us to be able to determine the symmetry. But the reality is, remember, it's the shape. You have to have an asymmetrical shape and polar bonds. Just because it has a lone pair doesn't necessarily make it polar. It's the asymmetrical shape. Just most asymmetrically shaped substances have a lone pair on the central atom. So it's asymmetrical. It's just a wording thing, but it's an important wording thing, especially in AP. So what does that make this, polar or non-polar? Polar. Okay, SF6. I'm not going to put in all the lone pair on the fluorines. Okay, is this gonna be symmetrical or asymmetrical?
Symmetrical.
Symmetrical. So therefore it's automatically
Non-polar.
nonpolar. Are y'all seeing this? This is super important. You can't do the next thing if you can't do this thing. Okay? That's why I'm just trying to make sure. So ask questions, speak now, forever hold your peace. If there's anything that, how are you knowing this, or why do you do that? You know? Cl2O is gonna look like this. Symmetrical or asymmetrical?
Asymmetrical.
Asymmetrical. Even if you drew it like this, we're gonna say AX2E2, so what's the shape of AX2E2? Bent. It's not linear, it's bent. So it's not going to be symmetrical. So it's gonna be asymmetrical. It's got phone call in it. Now this one, oxygen and chlorine are a little bit closer. So it's gonna be polar, we'd still call it polar, but it's not gonna be super polar because oxygen's 3.44, chlorine's 3.16, only a difference of 0.28, which really falls into our non-polar kind of category if you actually subtract them out. It just means it's gonna be weak. It'll still be polar, but just very weakly polar. Okay, just barely. But we're not gonna get that technical. I'm just gonna have you look at phone call. If they're there, we're gonna call it a polar bond. But because this is two of the big ones that are close to one another, that's, again, we're full of exceptions in the world. But I'm not gonna worry about that. We're just gonna call that polar. The bigger the difference in electronegativity, the more polar it's gonna be. Any questions on the ones I'm about to erase them?
Number 4, what is it? Is it so symmetrical, non-polar?
Well, again, because it's an ion, polar and non-polar doesn't apply.
Just a symmetrical?
It is symmetrical, but yeah, we don't put polar and non-polar on ions because polar implies it's got a positive and negative end. Ions are just either negative or positive. I just was going through that one to say, if it were a neutral, that's an exception to where it would still be, even though it's got lone pair on the central atom, it'd be symmetrical and it'd be non-polar. All right, PCl5. 1, 2, 3, 4, 5. Lone pair. Now, just so you know, I don't like this because it gets confusing with bonds, but a way you can do lone pair is just draw lines. It goes way faster. Okay, but then it looks like there's bonds everywhere and it gets confusing, so I don't like to do that, but I'm just being lazy. Are there any lone pair on the central atom? What does that mean about shape? All the bonding atoms are the same. There are no lone pairs, so this is symmetrical. So that means automatically it is nonpolar. SF4. But we got a lone pair right there. So that's going to be AX4E. Anybody know off the top of your head what AX4E is? Yeah, that's right. You know what? Distorted tetrahedron or seesaw shaped. Okay? So it's kind of out of whack. So it's asymmetrical. It's got phone call in it. That's going to make it polar. Alright, so now here's a case. I think I did this one. That looks like this. It's AX2. It's linear. But because it's not the same atom on both sides, is it symmetrical or asymmetrical? Asymmetrical. Therefore, it's going to be polar. SeBr3, it's an ion, so we really don't have to worry about polar or non-polar, but would it be symmetrical or asymmetrical? It's going to be asymmetrical. Okay, when you already have it drawn out. Now krypton, Kr, tetrafluoride, okay? When you do all this and count all your electrons, you're gonna have 2 pair on the central atom. This is AX4E2. Symmetrical or asymmetrical?
Symmetrical.
This is an exception. This is a symmetrical molecule, even though there are lone pair on it. That's why we can't say it's asymmetrical, because it has lone pair. Okay, it's the shape that makes it asymmetrical. But most shapes, except for the AX2E3 and the AX4E2, are going to be asymmetrical. Yes, sir.
Did you say 13 was polar or non-polar?
13 is going to be neither, because it's an ion. Okay? So we don't make ions polar or non-polar. So is this going to be symmetrical or asymmetrical? Symmetrical, which means automatically, even though they got polar bonds, it's non-polar. They all cancel out. And then BF3. Since there are no lone pair on the boron, it's trigonal planar. It's going to be symmetrical, therefore non-polar. Are y'all good with that? Any questions at all?
12, how is it polar if there are no polar bonds?
There are polar bonds because you got nitrogen.
Oh,
So it's being pulled, this is 2.20, this is 2.55, this is 3.16 when you look at electronegativities. So the electrons are all being kind of drawn that way,
I just missed the end phone call.
okay? Any others? I mean, this is one of the more challenging parts, being able to draw the Lewis dot structures, figure out the shapes, be able to tell whether it's polar or non-polar, okay? You're getting in the deep water now. All right. So, now what we want to do, now that we know the shape of molecules determines the polarity of the molecules. Now we want to start talking about then, well, how does that affect the properties of the substance? Okay? How does that affect the properties? So covalent compounds, just have it. Covalent compounds can be broken up into two categories: covalent network and covalent molecular. Okay? Now, covalent network is a very small class of compounds. There's going to be 5 that you're just going to have to know. The only way you're going to be able to know it's covalent network is just to know the 5. Okay? The first one is everybody's favorite. It's a diamond. Okay? It's a diamond. Diamonds, anyone know what diamond is? Pure what? Pure carbon. So each black sphere in here is a carbon atom. But it's covalently bonded to 4 other carbon atoms. So it's all AX4. So if you could just kind of focus in on one, you'll see it's tetrahedrally arranged around each one. But there's no molecule of carbon. Instead, it's a network. When you think of network, like a phone network or airline network, it's just everything interlocking, connected to one another. And so it's a very orderly arrangement. This is what we call a 3-dimensional. It goes X, Y, and Z. Diamonds are the hardest natural known substance because of the strong covalent network. Instead of having one molecule, you have thousands and thousands or millions of carbon atoms all stuck together in one big huge crystal. Okay? So it's a 3-dimensional covalent network, pure carbon, but no molecules. So this is the first covalent network. The second one is your pencil lead, which has never, ever, ever, ever been made out of lead. It's made out of graphite. What is graphite made out of? You know what element is? It's pure carbon. This is a 2-dimensional covalent network. Notice that each carbon now is only bonded to 3 other carbons. This is sp3 hybridization, giving us tetrahedral arrangement. Okay? They have sp3 and are the hardest natural substance, so I did say that. Okay? Graphite is a two-dimensional covalent network. Okay? It's bonded to 3 others in trigonal planar. It's flat. You can see the layers. Now in sp2 hybridization, remember there's a p orbital non-hybridized. The p orbital is always perpendicular to the plane. The white sticks in here are the p orbitals that weakly bond the layers to one another. So when you're writing with a pencil, you're sliding these layers off of one another. Graphite is a great lubricant because it slides over itself very easily. Because the layers are bonded strongly X and Y, but the layers are bonded very weakly to each other. So there's a lot of motion.
So the sheets are strong and the layers are weak?
Yeah. Okay, so the layers slide across one another easily. It makes it a great lubricant. If any of y'all have ever done the Pinewood Derby in Boy Scouts or in any kind of, kid group, okay? When you put the car up there and they race down the hill and just kind of let gravity pull them, well, you gotta lubricate the wheels. They don't let you use like a WD-40. You can't use anything liquid. You have to use a dry lubricant. Well, everybody uses graphite, powdered graphite. Sometimes if a door lock gets tough and it's hard to make the key turn, it gets kind of a little rusty or whatever, you have a spray. You can spray in the dry graphite in there, and it helps lubricate and make it easier to turn. So you don't always want to put a wet like WD-40 into that, because then dirt will collect on it and it'll actually make it more grungy and clog up. But the solid, the powder won't. So diamonds and graphite, these are the 2 most common forms of covalent network. Now, y'all, this is what makes chemistry so incredibly cool. Graphite, cheap pencil lead, is pure carbon. Coal is pure carbon, just in an amorphous shape. What's amorphous mean?
It's not like a,
Doesn't have a defined order. It's just randomly arranged carbons. Okay? So coal, dirty, nasty coal, just carbon just kind of all mixed together, not hardly even bonded to anything. Or we get 2-dimensional, you get cheap graphite. But all you got to do is rearrange the carbons to where instead of being bonded to 3, they're bonded to 4. Now we get this 3D, now we get diamonds, the girl's best friend. Very expensive, pretty, all pure carbon. Just how the atoms are arranged, their molecular geometry determines their properties. It makes them completely different. To me, that's amazing how a little difference can make a huge difference. Anyway, covalent network, those 2. Diamonds and graphite, you memorize those. Okay, the third one is silicon dioxide, which is sand. I don't know why they don't have the 4th and the 5th one, so right out in the margin. I never do these notes. I generally don't have notes. I generally write them on the board and make you guys just write them. But number 4, notice that silicon is in the same family as carbon. So it's going to bond the exact same way, Si. Okay? And that's, by the way, that's what you call a comical prisoner. It's a silicon. Yeah, I'm here all day, y'all. So, silicon and carbon are in the same family, so they bond the same way. So, silicon also does covalent network, just pure silicon. And then, obviously, silicon and carbon can bond together, so silicon carbide, SiC. It's really a sick molecule. I'm just on a roll. Just call me Butter, because I'm on a roll today. I had a long weekend. I'm all rested and ready to go. And I'm not going to be here on Thursday, so I only have today and Friday. So my poor Monday, Thursday people won't see me for like 10 days. Because I saw them last Thursday, but they were off Monday. They won't see me this Thursday, so it'll be next Monday. Okay, silicon carbide, SiC. Okay, it's a covalent network. It's used. It's a strong. It's not as pretty as a diamond, but it's as hard as a diamond, and so they use it as an abrasive. You show like sandpapers and industrial things that need to have really strong something to grind. They use silicon carbide. Okay, so those 5 substances. If it's not one of those 5 substances, it's not covalent network. You know it's covalent network simply by diamonds, graphite, silicon dioxide, pure silicon, or silicon carbide. If it's one of those 5, then we know it's covalent network. Now the properties of covalent network substances, as we kind of know, think about a diamond, very strong bonds. They're bonded by covalent bonds, all in 3 dimensions, 2 dimensions, very strong. Therefore they have real high melting and boiling points. Very hard to melt a diamond. You guys remember, you've heard about Chernobyl, right? Chernobyl, in their nuclear, in the core, they had graphite, and the fuel rods were inserted into solid graphite. And when the accident happened, it got super hot and eventually caught the graphite on fire. Now it's really hard to catch graphite on fire, but once it does, it burns white hot and it's really hard to put out. Most of the deaths with graphite, with Chernobyl, were the firemen trying to put the fire out. And it just took them weeks of flying over with helicopters and dropping sand on it and just kind of trying to do whatever they could. But anytime they flew in, they were in this radioactive plume, and so they were all getting exposed to high levels of radiation. It was not good. Okay? Diamonds, we know diamonds and graphite, they're insoluble in water. They're generally poor conductors of electricity because they're neutral atoms, so there's no charged particles, so they can't flow. However, graphite is an exception. I may have shown you this already one time earlier in the year. Does anybody have a pencil lead that they'll share with me? I'll give it back to you. I just need the lead out of it. There you go, perfect. I'll give it back. Okay? So, this is graphite, right? Now it is mixed with a little bit of clay. That's what the number 1, number 2, number 3 is. How much clay do they mix to make out how strong? Those of you in art, I don't know if you've ever done a pencil drawing, but they have different graphite levels to where you can smear it more or less. How dark it is, how light it is. Anyway, right now, again, when I plug this in, the light bulb doesn't come on because of the open circuit right there. But I can take this graphite. Now when I plug it in, the light bulb comes on. So the graphite is conducting the electricity. So if you're ever stuck somewhere and you need to somehow complete a circuit, a fuse blows and you need to just make a make-do fuse or something, you can just use your pencil lead. And the best thing to do would be a wooden pencil, sharpen both ends, because the wood would insulate it, and then the electricity would flow through the middle of it. Okay? But graphite is an exception. Thank you.
So
Oh.
like, the outlet that.
You get shocked. And as a matter of fact, when I first started teaching, I thought I told this story already, but when I first started teaching here, there was a kid named Matt Layton. Okay? Funny part about that is he had a twin that I didn't know that he had a twin, and he wasn't in my class. So I'd seen Matt. I can't remember what his brother's name was. Probably Mark or something that was close to Matt. Maybe Pat. I don't know. And so, but I would be walking down the line. Hey Matt, he'd be real friendly. Hey Mr. Hobbs, how you doing? Then I'd be walking and saying, Hey Matt. He just kind of look at me and just kind of rude, just not hardly acknowledge me. And it wasn't until a semester that I found out there was a twin. So sometimes I was saying hi to Matt, and sometimes I was saying hi to his brother, and they didn't know. But anyway, Matt sat in the very back, kind of right where Harrison is, and he just did not. There's just no way the pencil is going to conduct. And he goes, if I stick this in the socket, it's going to shock me. I said, yeah. Now I don't recommend you do it, but yeah. He goes, no way, really? I said, I'm telling you not to do it, but if you want to do it, he, idiot, stuck it in the socket, burned the crap out of his finger as it shocked him, You know, he had to go home and tell his mom, oh, I burnt myself thinking it, you know, and I was thinking, oh, great, I'm gonna get sued or something, you know. But she must have known that he was that guy that would do something. But I do not recommend that at all. It does very much conduct electricity. All right, so, okay, so those are the properties of covalent network, high melting point. So notice that of the three substances so far, ionic, metallic, and covalent network, they're all high melting points, all going to be solids at room temperature. And we can explain that based upon how strongly bonded they are to one another. Oh, and by the way, what I was going to say with this is these electrons in here are what we call pi electrons, or the p orbitals that are perpendicular, forming the pi bonds, but they're delocalized. They can flow throughout the whole area in between the layers. And so because those electrons that are in there, you just get this cloud of electrons that get delocalized, they can flow all through the graphite. That's why it conducts electricity. All right, good stuff. But what we really want to look at are covalent molecular substances. Covalent molecular. Actually, I'm not going to write in here. I'm going to pull this down. That'll get rid of some of the glare. Don't get rid of all of it. Get rid of some of it. All right. Now, generally, covalent molecular have weak bonds holding them together. And we're going to talk about what holds water molecule to water molecule. Okay? So they have low melting and boiling points. They're generally liquids or gases. So anything that you see as a liquid or a gas, if you take a big breath right now, oxygen, nitrogen, they're all symmetrical molecules, non-polar molecules, small non-polar molecules.
It says low battery, but it didn't cut the video off.
And it stopped.
It's blurry.
Oh, I love it when it does that. You can plug that in right behind you, please.
I can't get to the.
Well,
They're not working.
it pretty much probably stopped it, but let's just see if we can not stop it. No?
I can't get to the low bracket to dismiss it.
Oh.
There you go.
All right, those of you at home, hey, we always have these technical difficulties. That's why I totally hate this virtual stuff. All right, so low melting points, anything. We're breathing oxygen. Oxygen's a small non-polar molecule, very weak bonds holding. We're going to talk about what holds those molecules together. Oh, crud. What holds those molecules together, okay? They're poor conductors. Think about water. Now, well, don't think about water because everybody thinks water conducts electricity, but it doesn't, okay? Sugar does not conduct. These are your non-electrolytes, the covalent molecular substances. They're brittle. If you hit an ice cube, it's going to shatter into smaller pieces. It doesn't flatten into a thin sheet, okay? Polar molecules and other polar solvents, polar molecules dissolve. I don't know what and. This and is wrong. Okay? Polar molecules dissolve in other polar solvents. The rule is like dissolves like. Okay? Non-polar molecules are soluble in non-polar solvents. Like dissolves like. Polar dissolves polar. Y'all ever taken your clothes to the dry cleaners? Yeah? I mean, you at least heard of dry cleaners, right? And it comes back in little plastic covers it, and you can kind of smell. But a dry cleaner does not clean your clothes dry. They just use a liquid other than water. Somehow, some way, the water, the polarity of the water, ends up messing up the clothes, or the dye makes it fade, makes it shrink. So the clothes, either the color or the material, doesn't respond well to water. So when you take it to the dry cleaners, they use a non-polar solvent that then is going to be more gentle on the clothes. They're just, and it's a chlorinated hydrocarbon, and they used to use carbon tetrachloride, CCl4, but they found out that caused cancer. So all the people working in dry cleaner, are having high incidence of cancer. So that one got banned, and now they've come out with a much more environmentally friendly, but it's still a carbon and chlorine, just a bigger molecule, it's more complex. Can't remember what it is, but it's a non-polar, okay? So these are the characteristics of covalent molecular. These are the things that form molecules: CO2, O2, N2, water, H2O, sugar, C6H12O6. All the things we've been drawing the Lewis dot structures for, those are all covalent molecular substances, okay? Any combination of nonmetals is going to be covalent molecular. They're all going to have these weak intermolecular forces holding one another, okay? As far behind as I am, I may have to make a video tomorrow going over these here, and your homework will be just to watch the video, okay? I just need to be able to explain these three. This is super important. These three types of intermolecular forces. Let me just go ahead and let you fill them in, and then I'll talk about them on the video. Okay? So this first one is called London dispersion forces. Now that's hard to write out, so we're always going to abbreviate that LDFs. Sometimes it's called an induced dipole, and I'll talk about that later. Okay? The second one is called a dipole attraction. Now, what do you think dipole means? Two poles. What type of compounds have two poles? Make it, it's simpler than that.
Polar.
Thank you. Say what?
Polar.
Polar molecules. Did you say it in the back? Is that what you were saying? You just gotta say it loud enough. You got masks on and I'm old. Okay? Just speak up boldly. So, in other words, it's a polar molecule attracted to another polar molecule. Because polar molecules have a positive and negative end. So the positive end of one polar molecule attracts to the negative end of another polar molecule, and that attraction kind of holds the molecules together. And then third, we have hydrogen bonds. And whenever we're talking about these IMFs, more than likely the answer is going to be hydrogen bonds. All right, so pay attention to classroom tomorrow. I'm not sure when I'm going to post the video. I mean, I'll come in and I'll be here at 8, but whether I do it right off the bat or not, I probably will, and try and just get it uploaded. Yeah, I just want to go through and explain these three and talk about the effects of these three. This is huge as far as the properties. This is why we have to know whether the molecule's polar or non-polar. Okay, because non-polar molecules only have this type. Polar molecules have this type and this type. A special few molecules have all three. And then that water is one of the special ones that have all three. And if it weren't for hydrogen bonds, water would be a gas at room temperature. Life as we know it on Earth would not exist. So these hydrogen bonds are very, very, very important. And I'll explain more tomorrow, but again, it's because of hydrogen bonds that it takes a tremendous amount of energy to heat water up, and therefore the water has all that energy and it cools down. It's because of hydrogen bonds. I had an incredible time in St. Lucia over Christmas in the middle of December, in the middle of the winter. It was 85 during the day and 72 at night, every night. It was perfect because the water surrounding it takes a lot of energy to heat up, and it just doesn't change temperature much. Therefore, the air above the water doesn't change temperatures as much, and that's all because of hydrogen bonds.
Where do we put the
Just hold on to it. Now you can't reach the button.